Hey, hello.
Hey, good morning.
So yeah, first of all, good morning to all of you. We have the croissant ready. We have the coffee ready. So the first question of all would be, can you hear us? If anybody could just quickly type that in chat that it works.
Ah, nice.
Okay, thumbs up here. And the other thing, maybe Enrica, you can play a note on the hardware real quick.
Yeah.
Are you hearing that as well? All right, thumbs
Perfect.
up all around. So everybody watching this after the fact, this was a live stream. Everything that happens. You know how it is. And this is also, of course, part of the Programmable Audio Workshop 2020 whole day. And yeah, what is this all about? We are, first of all, Roland and Enrica, we got introduced already. We're a couple of makers and making kits and DIY projects, and also making our own hardware. And we're using some of them as what building today. And so some videos with Faust running on a Teensy 4.0, Teensy 4.0, and yeah, we're running Faust on it. We have a Teensy 4 that receives MIDI via USB. The Teensy runs Faust code, producing the audio. We have a computer that sends MIDI via USB, and that acts as a relay, basically. And the MIDI that we play comes from a simple MIDI controller. Let me play you one of the videos real quick so you know how it sounds in a more musical context.
We don't hear sound, I guess.
Ah, wir hören.
The sound of the instrument is not working for us.
Yeah, we are checking. Ist das mute? Ist die Quelle mute?
Okay. Yeah, I'm sorry about that. We're just gonna skip the video part for now. I think it's on our YouTube channel if you want to hear it with sound. Sorry. Let's go to the cam instead, and maybe you can play some chords on it. Yeah, so this is all generated on the Teensy, and it's all made in Faust code. So it's a very simple polyphonic synthesizer, but it's already just something that spawns in code and runs on hardware. So and I think the big idea here is I think everybody that wants to do something in hardware in the end has to tackle like 3 problems. They need to be a musician, of course, to have the musical idea what they want to do. They need to be a software coder, so they can write the program, and they also need some skills in putting together the hardware. And so each of these things has become a lot easier in this combination. And while we know that this is not a finished thing in the end or a finished module in the end, it's a really, really good start to get into it. So let us walk you through what you need to actually build it. And we're starting, of course, with the Teensy 4.0. And yeah, we have one in hand right here. It's a really small microcontroller dev board with a really fast CPU, so you can, or MCU, you can run it at 1 gigahertz, I think. No, at 1 megahertz. So it's really, yeah, it's really a fast core. Then the next thing you need is the Teensy audio shield. So that's a small board that has the codec on it, and it runs basically what it does. The Teensy generates the digital audio, and then the codec translates that to an actual audio output. And this is one of the things we talked about before. So this is a really good converter, and you can get good audio quality out of it. So you need that board. So the next part you need are stacking headers. Let me zoom in on these again. Here they are. And can you show real quick how they go into the board?
Yeah, so we have a basic way of putting together a sandwich. We have the headers like this, and then we can put this into a breadboard, as you can see here. Yes.
Okay, so the next thing you need is basically the same thing, but with pin headers on top and on the bottom.
Yeah, and we put them in the Teensy like this, solder them on, of course, from the other side, and then can we can have every pin outbreaked as well to put in some potentiometers or sensors or other stuff.
All right, so the next thing we'll need are jumper wires like that. So basically those connect on top of the pin headers. So you can, the pin headers you don't need for connecting the audio shield, you can use for other stuff like reading inputs and outputs. Yeah, there's some handy ways to do that as well, which we're going to show. Maybe just stack up that thing real quick, and let's have a look at how that's will work. Yeah, so there's the audio shield. In between goes the Teensy. And then attach like those jumper wires on top.
Yeah, they basically go on top. Or break out the left and right channel from the audio shield.
Yeah, you actually need to solder this, of course. We would workshop, but and we've like the whole thing already.
And for breaking out the left hand, here are some where you can put all your make with jumper wires.
Yeah, so the audio shield either comes with the headphone output, which is not so practical for your regular dealing with. So in the end, need the same. So we would always just break out the actual those, and for this you basically pins slotted together, and you can get them in the variety basically. And a really cool thing though that we want to show you, this is a mutant project as well. and she built these mutable breadboard friends, and the breadboard friends are little circuits that slot to breadboards.
Yeah, you can see it plugged in over here already. Here we have one not plugged in, and it holds 4 jacks to, and yeah, tip and switch of those jacks are available via these pins, and so it's very handy to plug in a jumper cable to connect.
Yeah. So instead of building the circuit on a breadboard, you would just plug in this pre-made PCB with 4 jacks already on it. Or there's other variants as well that have potentiometers. We have that just has 4 pots and a lot of jumpers. And every you build with pin header, you can just plug in, and we kind of really like this idea, and we started building our own sort of sub-circuits with that. For example, these are filters where you would just go and connect to the pin header, and then you would go have basically a test ready on a PC to the image. So you can prototype really rapidly.
Like Legos.
Yeah, hang on. So I want to show. Of course, these connectors, Donkey Kong. We just wanted to, because they're part. They're basically the connectors to hook up the patch cables, and they have a switch. So a really cool thing is that you can unhook. You can unhook your circuit if no cable is connected. So you can get rid of a lot of ground harm that way, just because of unpatching the inputs physically in circuit with no cable attached. Probably really convoluted explaining that, but great. You can get that with a great DIY store. And so the last obvious part here is, of course, a MIDI controller. We're using today an Akai MPK Mini, which is one of the cheap ones, but that has already everything you would need. It has note inputs. It has controller CCs, and it has some pads to play notes. And so this already has a lot for little money.
Yeah, and the nice thing is it has 8 jacks. 8 knobs. So you get like 8 parameters you can control.
Yeah, basically, and that also brings us already to one thing that's really, really different in hardware as opposed to software, is whatever you do, you will run out of knobs, right? I mean, you will have 8 knobs that control 8 parameters, and you have to find a way to sort of deal with that. And so in the way, like these MIDI controllers, really nice because they constantly remind you of, oh, if that parameter is not so important, maybe leave it out, or maybe lump it in with another parameter and make them interconnected. So we're going to talk about that later. And so the other one we wanted to talk about real quick, so this is a little higher end, but the cool thing about that is it doesn't only have it's a Arturia Keystep Pro, and this one doesn't only have MIDI, but also control voltage outputs. So that lets you hook into the modular world a lot quicker, because you won't only get the MIDI output, but you will also get voltage outputs, and done in a quite intuitive way, and still comparable to to sequencers that are in the Eurorec is still comparatively cheap. I mean, like Eurorec sequencers can get complex real quick and are produced in really small numbers, and then they start to get really expensive.
Yeah.
So this might be if you want to splurge, this is a nice one. And so yeah, the next thing we want to talk
software.
Yeah, the software and how the architecture, basically, how are we building it?
Yes. So do we want to first show the software bits or?
No, just
okay. Yeah. So how are we building it? So basically the heart is built in Faust. There we are building a simple oscillator, which we will show later how we build it. And in Arduino, we are then using multiples of this one oscillator for the polyphony. And also we are reading pitch and gate from the MIDI controller and setting envelopes for the Faust oscillator, like ADSR, with our MIDI CC commands. And then we are mixing all those oscillators together to one stereo output. And that is done by the Teensy audio library. Yeah, so that was like the software part. And in hardware, we are using MIDI. The MIDI is generated with our little keyboard, and we are hooking it up to a PC. And also we are hooking up our Teensy as a MIDI device to a PC. And at the moment we are using MIDI OX for patching it together. But you could basically also use a DAW or some other MIDI loop program, basically.
Yeah. So again, if you play some notes.
Yes. So I don't know if you can see it. This is the MIDI OX on the screen. Okay, I don't think we can see it. Okay.
Yeah, but what you can see there is that the MIDI notes are relayed via the computer. And so the Teensy actually offers you pins on the underside to make it a USB host as well. And that would probably be the next step that you wanted to take to just make it a USB host. But then on the other side, it's really, really nice to have the computer to have a quick look whether the messages you're sending are actually the messages you wanted to send, and it's a nice control step between. And honestly, for the whole development part, you have the computer there anyways. But of course, there are a lot of steps you could then take to make it more of a standalone thing. So and basically making it a MIDI host, making the Teensy a MIDI host would be one of those things. If you don't want to go that route, you could also go ahead and make a hardware MIDI connector that uses the UART port. And the code for that would be quite similar as to what we show right now. So one really quick thing, we published all the code. So if you want to follow along after the fact, hang on a real quick.
Yeah, you can see the GitHub link.
You could go to our GitHub. It's github.com making sound machines, and the repository is the only one in there at the moment. It's Faust on Teensy. And we made two directories. One is additive synth _Faust. This contains the DSP code. And we went, we went through it and commented in a lot of things. So if you have any questions about how that works, it's in there, and we're going to explain it, of course, as well. And then we have the Teensy code, which is already the generated code from Faust thrown in with the Arduino code. So this, if you install the stuff that we're going to talk about later, will hopefully just compile and upload to the Teensy Arduino. And yeah, I mean, GitHub, if you don't know it, you can just download the code as a zip from here. And so the very first thing we would show you is how the Faust DSP code that's sitting here will look in the Faust IDE. And so, yeah, I mean, I guess most of you know this one. This is the online version of the Faust IDE, and it's available at faustide.gram.fr. And because we noticed that in previous talks, it was really, really hard to actually see the code, we put that code on slides for you. So, but first things first, here's what we're trying to achieve. We're building in Faust, we're building a really simple voice. So this will become one voice in our polyphonic patch in Arduino. So as you can see, it's parallel processing 8 different partial harmonics, but this is going to be one voice. So we're going to have this 8 times in the end. And the Teensy will in the end run 8 by 8 of these harmonics, so 64 harmonics. Yeah, this is something we pulled from the Bela examples. So there's not that many examples for Teensy, but the Bela examples are really, really nice. And if you take our code and substitute the Faust code for some of the other examples, you will be able to run really nice stuff on the Teensy as well. Of course, there are some memory constraints. The Bela is based on the Beagle board and it has a lot more power, but it's also a lot more expensive. So I think it's a great trade-off. Faust IDE I showed you already. That sits at faustide.gram.fr. And it's really, really nice. You can run the code in your browser and just see.
Yeah, you can see beforehand if it breaks or if it makes the sound you imagined to make. So that's very nice.
Yeah, so that's really cool. And what you need to do is you need to paste the DSP code into the window there and then give it a name. We called it Faust additive.dsp. And you just have to keep in mind that the name you put in there, you want to name this nicely because you're going to need it later if you want to integrate it into Arduino then. Yeah, so the first thing here is the Faust code oscillator.
Yes, so
yeah, so the thing is here, we lowered the resolution of the sine oscillator in order to make the computation easier on the Teensy MCU. So for that, you use read table, and then you basically just reduce the table size by 1 bit. Yeah, that actually makes the code a lot slimmer. And as we're running, like we said, as we're running a lot of sine waves there, this is a good compromise to just deal with it with more efficiency. Then the next thing here is setting up a user interface for gate, frequency, and gain. And one thing to note right here is that, okay, so you have the blue variables. They are the variables you use inside Faust. And you have the orange variables. These are the variables you will going to see later in Arduino. So it's your choice if you call them the same or call them differently. We figured out for us it's easier to call them the same thing because you don't get confused what you're actually doing. And yeah, so just remember blue variables are inside Faust, and the names of the user interface objects, which are in orange, that's what you're actually talking to in Arduino then. The other thing you can see here is that you set the default values here. For example, for the frequency, the default value is 440. And then you set the limits of the frequencies, so which the lower limit is 20 hertz and the upper limit is 20K. And you just have to keep them in mind because, of course, in Arduino, you could set things outside those limits, and then you might run into troubles of just stuff not behaving the way you wanted. We didn't have any bad crashes, but you're just going to have stuff like notes ringing too long, or I don't know, frequencies clipping at the top range or something like that.
Yeah, or the knob has a strange range.
Yeah, so just keep that in mind. You're setting the limits of your DSP code already here, like the nominal limits you want to achieve. So the next thing we implemented here is a filter, and I know that is uncommon for additive synthesis because you don't usually do that. But we figured out that it's really, really fun to play, and it makes it can carve out the harmonic resonances really, really well. Maybe you want to.
Yeah, and also we using a resonant low pass, and the resonances are very fun to play with. So
yeah, maybe you want to play a couple of notes. And if you sweep through the macro. Yeah, you almost get like Formanty type sounds out of that, and I think that's also a nice point about making hardware modules. Apart from the theory that's behind the instruments, you also have to find stuff that's fun to tweak and fun to play in the end. So, and that gives you a little bit more freedom and opportunity to carve out the sound. So then the next piece of code here is the harmonic oscillator. And this is really interesting part of code because it uses an iterator range that is triggered later with PAR. PAR does parallel processing. I can show you that in the main function in the end. And so what range does, it just creates instances of the user interface for the ADSR for each of the partials. So we're going to create 8 partials. Each of the 8 partials has the ADSR in the end. You will get a user interface for the volume for each of the partials. And in the Faust UI, they're represented as sliders. So if you hit run in the Faust IDE, you can already play with those. Arduino doesn't care if you have a slider or a number entry or whichever of the user interface types. So you can just choose the one that you like best for that here. And the other thing that's interesting here is that the parameters are smoothed, so you don't get steppy response from your knob inputs in the end. So then at the end of this code is the process part, and this is where the whole where the whole code comes together. You parse with parallel. You parse through 8 instances of the harmonic oscillator. You combine them all together, and then you run them through the resonant low-pass filter, and that's basically our patch here. So again, here's which parameters we will have in the end in Arduino. We will have the gate, frequency, and gain, and they set the fundamental pitch of the harmonic oscillators, while all the other partials are whole number dividers, no, whole number multipliers, so ×2, ×3, ×4, and so on. We will get the gate, the node on or off. We will get the gain, which is the overall volume. We will get the filter frequency and filter quality. We will then get the filter makeup gain, which is just something you can play with to counter like peaks and also the drop-off in perceived volume. And then the fun part here is with the this percent range iterator. Faust makes you a user interface for all 8 instances starting with 0. You get volume 0, volume 1, volume 2, and so on up to volume 7. And these are for one instance of the generator. These are, the individual volumes per sine wave, basically. So here's where you can really play with the harmonic oscillator. And you can also get the same thing for the ADSR. So you can set each of these ADSRs per sine wave separately. So just note that in the end, we will also have to set for 64 sine waves, we will also have to set 64 parameters here. So you will see in the Arduino code, just to keep things easy to read, there's a lot of granny coding where like blocks of code are duplicated and copy pasted just to image or just to mirror that you're setting the 7 parameters here and done. I think that sometimes help if you look at it. And then, of course, last step you will need to do in Faust is you need to export the code. And for that, you get the, you make sure you have selected your project here, the correct DSP, and then you hit the little truck, and the export should be set to Teensy and Teensy as architecture. If you hit compile, you will get the download button. And once you downloaded everything, you will get the binary.zip, which actually doesn't contain a binary, but contains a text file C++ and the header file for that. And these two you drop in the same location as you would set up your Arduino project, which is, if you look at the GitHub, that's what we already did for you here.
Yeah, it's the same folder. So we have a folder named like your Arduino sketch. Then you have the .eno, and in there you also have the C++ and header file. Yeah,
so these actually just go into the folder, which is really cool. So that's really great integration, and it's really quick. And so where are we here? So now we're basically done with the Faust part.
And next we would show how to set up all the parameters in Arduino.
Yeah, so first things first, what you need is you need to install the Arduino IDE. It lives at arduino.cc. It's a simple install. Then you need to install the Teensy libraries. Those you can get at Paul Stoffrigen's website. That's the guy who makes the Teensys and designs them, and also offers a lot of code. So it's a really nice site. Sift through there, see what you can find in terms of libraries that are already pre-made for Teensy. It's great stuff and really well prepared, and good examples too. And then there's one special thing that you need to do. You need to go to the Arduino folder, your Arduino install, and you need to change the linker for Teensy 3.6, 4.0, and if you have one 4.1, from GCC to G++, just in order to for the Faust thing to compile and link into the project correctly. And there's a much better explanation for that at this URL at faustdoc.gram.fr. And there's tutorials about the Teensy, and then there's this special note about the Teensy 3.6. Let me show you that real quick. The page looks like that. And there's a description what you need to change in order for that to compile. And I know this has been a little stumbling block for just people trying this out, so make sure you do that. Otherwise, your code won't compile. And so the first thing we would look at here is the overview, basically, of what we're trying to achieve. This is not really code, but this is basically a quick, dirty overview of what we need to do in the code, so just that you know what we're talking about next. So the first bit is we want to import the audio shield, and we want to import the code from Faust. We want to then create 8 instances of the Faust harmonic oscillator, and we want to group them together, n and n plus 4, so voices 0 plus 4, 1 plus 5, 2 plus 6, and 3 plus 7 make up one voice, and that's so we get this nice detuned analogish sound. Do you want to play a couple of notes?
Yes.
So there you can hear you have this nice chorusy thing, and that's because we use two harmonic oscillators per voice, basically, and they're slightly detuned like they would be on an analog synthesizer, and so you get a much less static sound. And that's a theme you will also hear throughout this talk, that we try to sort of break up a little bit the stability of the sound by detuning things, and also giving a little bit of leeway to the parameters. And there are already easy ways to do that. Then what we want to do is audio library stuff. So this hooks into Paul's code. We want to use the Faust harmonic oscillators and route them to the individual left and right channels. I'll show you in a second how that works. We will want to set up MIDI to note frequency conversion, or MIDI note to frequency conversion, which what that means is I'll also show you later. And we want to set up the polyphony. And then comes the setup loop in that, or setup function in that we want to just set the mixer gains, enable the audio shield, define the handles for the USB MIDI callbacks. So this is really good functionality, because in the loop, then you just say you want to read the USB MIDI. And what that does is the loop is basically free, or and the audio processing is done the whole time, but inputs are only processed if a MIDI note comes in. So what you want to do there is catch the incoming events, and then you got the handles, the MIDI note on, MIDI note off, and control change. these take the three variables that MIDI provides you with: the channel, the note, and the velocity. And you catch gate on or gate off there. You catch the pitch, and you want to handle the voice allocation there, just so that you don't run into problems with how many notes are pressed, and if somebody's pressing the same note over and over again. And so you need a bit of code for that. And then the most interesting thing are the control changes. We have 8 CCs here, and we set 1 to the volume of the fundamental, and there's a nice trick to that as well. We set the next CC. We do a macro. We set the volume harmonic 0 to 7. In CC3 and CC4, we do the center frequency filter, and the 7, the sustain, and 8, the release of the ADSR. So let's just look at the code real quick, how that works. You include the audio library. You include Faust additive.h. This is the header file from the Faust export. Then you instantiate just the I2S and the chip itself that's on the audio shield. So that's code that just gets those two running. And then comes the interesting part about the Faust integration. What you do here is you make 8 instances of Faust additive, and Faust additive again is the DSP code that we got from Faust, and you just give them variable names. So we just call them additive synth 0, 1, 2, 3, 4, 5, 6, 7. And again, what we want to do in the architecture is combine 0 and 4, 1 and 5, 2 and 6, and 3 and 7. So here is the mixer stuff. This one really cool thing is you can actually go to a graphic user interface tool at Paul Stoffagen's site. It's pjrc.com/teensy/GUI. And there you can generate basically this sort of patch for you. And this is already very familiar for people who are into modular synthesis. What you do is you create mixer objects, and then you hook up the ins and the outs. And I've pasted a little screenshot here. Basically, we mix the additive synth 0 to 3 together in a mixer of 4, then 4 to 7 in a mixer, and then we need to recombine them. So the Teensy mixers always have 4 inputs and 1 output. So what we are doing here is once for the left channel and once for the right channel, we're combining the inputs and sending them to the left and the right channel. And yeah, I mean, this is a bit tedious stuff in the code in the end, and it's a lot longer here. So whenever you see the dots in our pasted graphic here, just know that there's a lot more of the same code basically there. But the gist is make mixers, make patch codes that connect a mixer in and a mixer out, and then it results in the signal flow that you see on the right here. So the next thing that is set up here is the note number to frequency. It's an array that just tells all the 127 MIDI note numbers which frequency actually corresponds to which note number, And it's the, yeah, I don't know, it's note number 0, C0 is 8.18 hertz. That's how you read that. We commented the note names above that, so you can actually check for accuracy. You can add decimal points if you want it more accurate. And so here's the first real neat trick. We make a function to set the ADSR. And so we have control over each ADSR for each of the harmonics, which is really, really cool. And so that does mean we don't need to set them the same value, right? So what we do here is we get the value that's going to be the 127 from the CC. And then we do some math here, which is explained on top. But what we want to do is convert it to a floating point value between 0 and 1. And what we then do is add a scalar, just a multiplier to some of the values. So what happens here is for the fundamental, the attack is the longest. So the fundamental needs to, the fundamental comes in the slowest fashion, and then the highest harmonic comes in really quickly. Maybe you can again play single notes. So what you can hear here is that you can actually get a timbre change just over the attack, which is really, really cool. So that makes it lively again. We do the same thing for the decay, just the other way around, so it evens out before the sustain. And yeah, the way you set the parameter values is then just by addressing the Faust instance, Faust additive synth O dot set param value, and then you address the value we discussed earlier, which is decay 0 to decay 7, and then you give it a value. Then there's the sustain values. We keep them at the same level because the thing with the overall values we already did in the mixer. And for the release, we again do the same thing. So, okay, so the next thing I want to talk about, and that's a really, really cool concept, is having macro knobs. And what that does is you want to set the whole timbre of the harmonic oscillator at once, but you don't have a slider or knob to set each of the volumes, each of the 8 volumes individually then. So instead what you could do is to map those onto a single knob that goes from 0 to 127, and then, for example, make harmonic 1 loud in the beginning and soft or off in the end, but harmonic 2 do the inverse, be soft in the beginning and loud in the end. And harmonic 3 starting soft, then going loud, then going soft again. And then more variations of that, as you can see in the graphic here. The higher you go in this graph. And what happens there is that you get different combinations of timbres as you move along the knob. And is of to Gissel and looked in so and so about the value and we the midi callback and we're here we're seeing so stored node -1 means the node is off, so we're looking for the first instance in the array of 4 nodes that is -1. Then we're setting that array to setting that to the node, so we know, okay, well, node 1 is C0, and then we're assigning one voice to each of those numbers in the array, basically. So voice 0, you can read it as voice 0 has synth 0 and synth 4 assigned. Voice 1 has synth 1 and synth 5 assigned, and so on. And so this is basically polyphony code. And again, here you do that on my node off. You just switch those off again. If you find that the node off is the same as one of the nodes that's already in the array, then you switch it off and set it to 0. And then the, well, most interesting part here probably is the my control change. What does it goes through the cases CC1, CC2, CC3, CC4, and so on as the on the midi, and you set something to be spread out of function. For example, the volume on the and then there's also in this just going to the set marble, catch the value and yeah, put it in the function. And so this is the code in Arduino. We need then to flash the code onto the Teensy. We need to connect the Teensy with a USB cable. Be sure to make it with a data cable. We need to connect the Teensy 4.0, and we set it to 816, which is a little overclock already, but runs really smoothly and doesn't get hot. We need USB type serial plus MIDI, and then we use the arrow to compile and upload. Let me show that real quick here. You just go here, and then you have either compile or upload. You hit the compile, it goes through a whole deal and starts compiling that, and then you can upload it to your Teensy, which we've already done, of course. So what is happening then is then you can combine the whole thing with Modular.
Yeah, so I think our time is almost up, but we have a little patch which we would play real quick for a minute or so, right?
Yeah.
Yeah, so this is again the like try sound. And now I will patch it in some modules for basically effects.
Yeah, so what we're hearing now is running that into an amp, and then we use multiple instrument streams as a VCA. We use this not rocket science wobbler to make the nice wobbly sounds. And we use the Plinky, which is great DIY project, to add the cool reverb. And so that's it from us. Maybe we have some time for questions, but if we don't, then let us know.
No, sure, we have time for questions. And thank you very much, Enrica and Roland, for this very nice and very close to what we would have done if we were not in this special configuration that is a hands-on workshop. And so with all the camera, etc., I think we have all the information to redo that by ourselves. That was really, really nice. So we have time for questions. Do we have questions on the chat, or if you want to speak, please unmute your mic and speak and ask your question directly.
Let's see.
Okay, then I will start with one question about this set volume macro. How this, I think it's, as you explain, as soon as you are using real hardware, you run out of knobs very quickly. And so this is a way to control multiple parameters with just one knob. How the idea came from, and how effective is it? How easy is it to use?
The thing is, actually a lot of modules in Eurorack do that.
Okay.
A lot of the DSP-based modules, especially, of course, because you always end up with code that has a lot of parameters you can set, and you just need to choose a user interface in the end that produces a nice result. And I think there's already a choice in there, very much like what Max said in his talk, that you're building an instrument and it will be tilted towards a certain use. So, for example, here we thought, okay, you want to control the volume of the fundamental, because that's really a part of how weighty the sound is. But then you want to control the timbre maybe as a whole. For example, on a hardware knob, depending on the resolution, you would have much more resolution. For example, 4096 steps, and then you could fine-tune that a lot more. But the overall idea that you group together parameters is really nice, because it also lets you play the instrument in a different way. There's some great examples of grouping attack and decay, or attack and release together on macro knobs as well, and you just start to set the envelopes differently as you would an ADSR envelope. So if we introduce two more parameters here, we have to, of course, give up two knobs of the ADSR, for example, and then you would just think of a nice way to still be able to use the parameters in a good way. Does that somehow answer the question?
Sure. No, that's really nice. There are other ways to control multiple parameters. For example, I don't know if Thierry, are you still here? Thierry Caron? Okay. We we did a software with Thierry many years ago where which was inspired itself by a software developed at GRM. And the idea is that you represent all your slider or knob on a 2D surface, and the value of the knob is the distance between, so you place all the knobs on this 2D surface, and the value of the knob is the distance between the place of the knob and the center of a cross that represents the center. And then, so you can move a slider close to the center or far from the center to change the value, but then you can move the center itself and change all the slider at the same time. So basically you do a two-dimension projection of a n-dimension space, and you can change the projection by moving the knobs, the sliders, but you can explore the projection by moving the center itself. So that's something that can be done with a joystick, for example. So that's a really interesting questions, I guess.
Yeah, that sounds great, and that's I think something that can be explored nicely in Rec. Just because there are a lot of so for example, if you would imagine the knobs as CV inputs, which we didn't have the time to show like the circuitry behind it. If we wanted to show the circuitry behind building a whole module, then it would probably be like 10 of those workshops.
Sure.
Yeah.
But there are then, of course, modules that just do user interface. So there are modules that do joystick. So if you basically this matrix or XY axis projection that you talked about, that you could potentially do by hooking up a joystick module and plugging in
a CV input.
In a CV input, and
or
then
multiple CV inputs.
Then you would possibly get that plus the macro knobs. So so it I think it's really nice in Eurorack or in Modular. You can sort of choose your control paradigm separately from the module itself.
I have a question on the cost of all the stuff that we can see here, and in particular the module made with the Teensy. How many euros do you have to spend for that?
So I think the Teensy itself is like $20, maybe.
Yeah,
around 20. The audio shield, I think also like $20. Yeah, then pin headers, that's like penny stuff, you call it, I think. This we saw the connector to Eurorack, we soldered ourselves.
Yeah, so these are not available at Mutable Instruments, but they're open source. You can either order them yourself, the PCBs, and then you need to solder in pin headers and the jacks. But you can also buy them pre-made. I think Pusherman Productions has them, and there I think 6 boards are €9 or something.
Yeah. So yeah, in total I think like 55 euro.
Yeah, something around that. There's also, of course, other alternatives to the Teensy. For example, this is the Daisy board, and that's geared a little more towards, or that's geared completely towards audio development.
Yeah.
And we'll have Andrew Eikenberry talk about that, I think, in the last talk today.
Yes.
And it's a really, really great platform as well. So that would combine basically an audio shield and a microprocessor. And so, what was that? It was like $25 or something. So that's really great
Yeah, but
price point.
it has the audio codecs on it,
Mm.
so no need for a
Yeah,
external
you don't need an
codec.
external board for the audio. Mm.
Yeah.
So, do we have any question from the audience? No.
I see a lot of chat about cool stuff we need to check out. Thank you everybody for that. So that's really cool. We're going to have to look through that as well.
So last question, because unfortunately, sometime at least from my point of listening, the audio was not always perfect, and so probably is not going to be perfect on the YouTube stream. But I guess you did a registration of your own of the presentation that will be available somewhere.
Yes, we did that too. We tried to stream the whole thing in parallel on YouTube, so it's going to be on our YouTube channel.
Okay.
If everything, if all fails, we will probably just re-record it.
Yes.
I mean that would be another option.
Yeah, I'm sorry. The technical condition obviously is what it is, and especially for the audio, when you are just making a presentation with PowerPoint and voice, it's okay. But here we are in a more demanding situation, and it's far from perfect, unfortunately. But this was so packed of very useful information, so I think that that was really very interesting. So thank you
Thank you for having
Roland.
us.
Yeah.